Again, this is a lecture for design of unreinforced masonry walls under vertical loads. So the design of masonry walls should satisfy the code requirements in order to safely carry the vertical loads without experiencing any of the following failure modes. So our design here is based on designing for several modes of failure. First is the partial failure, which is due to bearing and or moments together. Second, the instability, which is due to buckling and or moments. Finally, which is the progressive failure, which could be due to any of the above, by the way. One failure could initiate another failure, so it could be what we call the progressive failure. So, but there is a very important concept that is stated by most of the codes, including our Egyptian code, which is that the design of masonry structures subject to eccentric axial loads does not allow any tensile stresses. So if you are talking about axial loads, a masonry structure supported to axial vertical loads, it is not allowed to have any tensile stresses. So the tension should be zero. So the effective height is a very important thing here that we need to understand. The effective height of our wall. So if you go back to the concepts of the buckling, the Euler buckling concepts, and all that stuff, the effective height, it is equal to the height if you are having a hinge to hinge end condition. However, if the end condition is fixed free, it is double height. If it is fixed hinge, it is, if you calculate the buckling theoretically speaking, it is 0.5 h. However, practically speaking, theoretically speaking, it is 0.7 h. However, practically speaking, you take it as 0.8 h. Fixed is something extremely rare to find. This is why it's not included here, because it's not practical actually at all. So, on the other hand, when you are talking about a load that is concentrated, and this concentrated load is distributed on maybe a plate or a bearing surface, could be a plate, could be a piece of wood that is resting on a wall. Disregarding whether this wall is made from what, it could be made from anything, but the concept itself is that this could cause what we call the bearing failure. And while it is being distributed on the load is transferred to the wall, it is transferred through what is called the effective length. And depending on whether this load is acting on 1 point or 2 points, you have these two cases that you could see here. But typically the effective length is equal to B plus 4T, where T is the thickness of the wall itself. The slenderness ratio is a very important thing, because there is a maximum allowable slenderness which is 90. So this slenderness ratio is simply the smaller of H effective and L effective divided by the thickness of the wall. So the very important thing here is that we are not designing the wall to be a thin walled structure. We are not designing this wall to be a thin walled structure. Thin walled structure which is a very slender wall. We are not designing it to be a very slender structure. But in most of the walls that you will be facing, masonry walls designed typically at a height of 3 to 4 meters or something like that, you will not have an issue with this slenderness thing, okay? Because maybe even if it is 5 meters divided by 0.25, so this is a 20. I mean, it's not exceeding. In most of the cases, you will not find something exceeding a 90 in terms of ratio of slenderness. Okay. This issue of the effective area comes into the picture when we are talking about the concentrated load. When we are talking about the concentrated load, the effective area of the plate that will distribute this load on the wall is very important. So if this area covers the whole thickness of the wall, this is simply the area of the plate, so it will not change. However, if it is only covering part of it and it is not acting at one edge, then we are talking about a certain area which is function of 45 degrees plane. The 45-degree plane is very important here because this is what we call the shear plane. So this is the plane of failure, or the shear plane and the bearing plane both are actually acting at 45 degrees. So this is the plane of failure that will be caused by bearing here. Okay. So in such a case, we'll apply this equation. So it's A1 is multiplied by root of A2 over root A1, which should be less than or equal to 2 times A1. That takes us to the design for bearing. The allowable bearing strength is simply equal to 1/4 of the masonry strength, which is F dash M. So this is 0.25 F dash M. The axial compressive stress actually is simply what you know from mechanics, which is P over A, effective, the effective area. The bending stress, as you know it, it has a positive and a negative sign because at one side it will be tension, at the other side it will be compression. So it's plus or minus my over I. This again, this is something that you should know from mechanics of materials. To guarantee that no tension happens, which is a very important thing that the code states, FA should always exceed FB. FA should always exceed FB. So if FB is more than FA, this is considered as a tension failure. For sure. Automatic failure. Okay? And FA plus or minus FB should be less than FBR. So even on the compression side, the summation of the magnitudes of FA and FB together, it should be less than 1/4 of F dash M. After that, we'll be designing for stability. So here we are talking about a small FB and a capital FB, and a small FA and a capital FA. The smalls are the ones that we have calculated up there, but the capitals are based on the material and the geometric properties. So the allowable axial strength, FA is 0.25 F dash M multiplied by 1 minus H effective over 140 R squared. What's this R? The R is the radius of gyration, which is simply I over A effective. This will tell us and this will take us also to the allowable bending strength, which is FB, F capital FB, which is F dash M over 3. So simply you are having the ratio of bending plus the ratio of axial stresses. If they sum up to less than 1, that means that this structure will not fail due to stability. Last but not least is the buckling. Buckling depends mainly on, this is the critical buckling load. This is the Euler buckling, by the way. I mean, this equation is the Euler buckling equation for an eccentrically loaded structure. So EM, the modulus of elasticity of the masonry, multiplied by I, multiplied by pi over H effective squared. All that is multiplied by 1 minus 0.557 E, which is the eccentricity, over R. the radius of gyration, all cubed. And again, so simply if you don't have an eccentricity, if the E is 0, so simply it's E I pi squared over H effective squared, which is the typical Euler buckling that you all know. However, if you have an eccentricity, you will have that term coming into the picture, and you will notice that this term will highly affect the values, typically depending on the range of the ratio between the E and the R. And this critical buckling load, you should divide it by 4, and this is the maximum axial load that you are allowed to carry in order for this thing to not buckle. And if you ask me what's the most common to see, the most common to see is the tension failure, actually, and the critical buckling failure, if you are talking about something with a high eccentricity. But if you don't have eccentricity, anything of that is possible, actually. The bearing could be even more critical in some cases. So let's take an example. Check the safety of a masonry wall made from sandstone blocks 200 mm by 200 mm by 400 mm. If the wall height is 3 meters, the width is 400 mm. The wall rests on an RC ground beam and carries a 10 kN ultimate load acting on a base plate 300 mm by 300 mm with a 50 mm eccentricity at the edge of the wall. Consider a prism strength of 4 megapascal. First, you need to sketch this thing. You have if you have an assumption that we have an hinged end condition, which is valid because you are having one ground beam at the bottom and a ground beam at the top. So here you could assume it's a pin-pin connection. So in such a case, the H effective is 3 meters. The L effective is B plus 4T, which will give us 1.9 meters. So lambda is 1.9 over 0.4, so this is 4.75, so this is 90. So the dimensional condition is satisfied. The bearing check, A effective is 300 by 300, this is 90,000 millimeters square. I is 300 by 300 cube over 12, so this will give us 675 million millimeter per 4. M is P times the eccentricity, which is 10,000 times 50, so this is 500,000 Newton millimeter. FBR is 0.25 F-M, so this is 1 megapascal. FA is P over A effective, so this gives us 0.11 megapascal. The small FB is My over I, so this will be also 0.11 megapascal. We are very lucky that this thing got us exactly two equal values, which means zero tensile stresses. So if FB was slightly larger, it would have failed due to tension. On the other hand, the summation of the two values will give us 0.22 megapascal, which is less than the 1 megapascal, the FBR. So this is safe for beam. Furthermore, we should check the stability. R is equal to I over A effective. So this is 27.38 millimeter. FA is 0.25 F-M multiplied by 1 minus H effective over 140 R all square. This will give us 0.388 megapascal. FB is 1/3 of F-M, which is 1.33 megapascal. So let's calculate our ratios. So the small FB over the capital FB plus small FA over capital FA. This will give us 0.369, which is far less than 1. So the stability condition is satisfied. Finally, we check for buckling. So EM from the equation in the table in the code is 700 F-M. So this is 2800 megapascal. P effective is EMI multiplied by pi over H effective square multiplied by 1 minus 0.557 E over R all cube. So this will give us negative 10.9.4 Newton. Of course, a negative value, this is unrealistic. That means that for sure it's unsafe for buckling. It could not even carry itself, could not even carry its own weight. So this wall is unsafe for buckling. It will buckle under any conditions. And if we think about it, why is that happening? Of course, it will happen because you are having a 4-meter high wall without even a lintel in between. A lintel is what we call in Arabic ataba. So you have something very high without anything to support it in the lateral direction. So it has already a high buckling length, which is, sorry, 3 meters, not 4 meters. But so, and it has a high eccentricity together and an eccentric load. I mean, if the load was concentric, life would have been different in such a case. But you are having an eccentricity and a high wall without lateral support, you are having a problem here. That's it. Thank you.